Welcome dear learners. We are continuing Unit 2 Chemical Bonding and Molecular Structure. In the present module, we are discussing lattice energy and Born-Haber cycle. The contents of this module are lattice energy, factors affecting lattice energy, Born-Haber cycle, illustration of Born-Haber cycle, solubility of ionic substances, partial covalent character of ionic compounds, and problems based on these concepts. First of all, lattice energy. Lattice energy, abbreviated as U, is a measure of strength of the force that hold the ions together in an ionic solid. It is a measure of the stability of ionic solid. Lattice energy of a crystal is simply defined as the amount of energy released when 1 gram mole of the crystal is formed from its constituent gaseous ions. When positive and negative charge ions come together to form an ionic solid, there is a decrease of the potential energy. Hence, during the formation of an ionic solid from the constituent gaseous ions, a certain amount of energy is released. That released energy is termed as the lattice energy. This is the illustration of the liberation of lattice energy. A and B are two oppositely charged ions. They will combine together to produce the ionic compound AB with a fixed lattice structure. As a result of the formation of AB, there occur the liberation of energy. That liberated energy is termed as lattice energy. So, this energy released, the lattice energy released, is numerically equal to the energy that will be needed to convert 1 mole of the same ionic compound into gaseous ions. What this means is, when an ionic compound is produced from its constituent ions, energy is released. You have to supply same amount of energy to the ionic solid to separate it into ions. That energy is also similar in magnitude with the lattice energy. So, you can define lattice energy in two different ways. The first way is like this. It is the amount of energy released when ionic crystal is produced from its constituent ions in the gaseous state. That is the most common definition. In an opposite way, you can define lattice energy as the amount of energy required to separate 1 mole of an ionic solid into its component gaseous ions. Both the terms are similar. Both depicts the lattice energy. Now, this lattice energy is different for different kind of crystals. For example, sodium chloride is associated with a lattice energy of minus 787 kilojoule per mole, which simply implies that during the formation of 1 mole of NaCl from 1 mole of Na plus gaseous ion and 1 mole of Cl minus gaseous ion, the amount of energy liberated will be minus 787 kilojoule. Similarly, lattice energy of magnesium oxide is minus 3791 kilojoule per mole, and that of calcium chloride crystal is minus 2250 kilojoule per mole. Higher the magnitude of the lattice energy of an ionic solid, the greater would be its stability. This is the relation between lattice energy and stability of an ionic crystal. That means stability proportional to lattice energy. Now, When positive and negative ions come together to form an ionic solid, there is a decrease in the potential energy. Hence, during the formation of ionic solid from constituent gaseous ions, certain amount of energy is released and this energy is termed as the lattice energy. Factors affecting lattice energy is another important area of this discussion. There are so many factors that affect lattice energy. The first factor is ionic charge. Higher the charge on the ions, higher will be the lattice energy. This is because higher charge on ions result in strong electrostatic force of attraction which lead to higher lattice energy. For example, consider the magnesium oxide ionic crystal, which consists of Mg2 plus and O2 minus ions. Their charges are 2 plus and 2 minus respectively, has a much higher lattice energy than NaCl, where the charges are Na plus and Cl minus. So, Mg2 plus and O2 minus are divalent ions. Na plus and Cl minus are univalent ions. Higher the charge, higher will be the lattice energy. MgO is associated with high lattice energy compared with the NaCl. Now, the second factor that governs lattice energy is ionic radius. Smaller ions allow ions to pack close together, increasing electrostatic attraction and lattice energy. So, small ions imply high lattice energy. For example, LiF is an ionic crystal with a higher lattice energy than cesium fluoride, CSF, due to smaller size of Li+. So, small sized ions imply high lattice energy. Now, the third parameter that governs lattice energy is the crystal structure. The arrangement of ions in the crystal lattice influence how effectively ions interact. For example, NaCl is associated with the rock salt structure, zinc sulfide is associated with the zinc blende structure. These two crystal structures are entirely different in their packing, in their orientation, in their coordination number, etc. etc. So, as the crystal structure changes, there do a change in lattice energy is there. Denser packing leads to high lattice energy. This means when the constituent ions are very closely or densely packed, there is an associated high lattice energy. Now, periodic trends in lattice energy. Lattice energy can be considered as a periodic property because it can have some periodic variations. That is, there is a trend in lattice energy as we move along the period or moving down a group. If we proceed across a period, that is from left to right across a period, the ionic charge increases and ionic radii decreases. As a result, lattice energy increases. For example, NaCl is associated with lower lattice energy compared to MgCl2, which is again less than aluminum chloride. These three ions are present in the same period. So, if we proceed from left to right across a period, there is a decrease in the lattice energy. So, this picture simply represents the variation of lattice energy across the period. From left to right along a period, there occurs a decrease in the lattice energy. Now, what is the variation of lattice energy down a group? As ionic radii increases, lattice energy decreases as we move from top to down in a group. For example, LiF is having higher lattice energy than NaF, which is again greater than potassium fluoride. So, there is a decrease is observed in lattice energy as we move from top to bottom in a group. Now, we are discussing the most important part associated with the determination of the lattice energy, that is nothing but a thermodynamic cycle known as Born-Haber cycle. The Born-Haber cycle was introduced in the year 1919 by German scientists Fritz Haber and Max Born. You are familiar with Fritz Haber, who is the discoverer of the Haber process for the manufacture of ammonia, and Max Born was a quantum mechanical physicist, and they together proposed the thermodynamic cycle known as Born-Haber cycle, which is highly useful for the theoretical calculation of lattice energy associated with a crystal. It is a thermodynamic cycle. Born-Haber cycle is a thermodynamic cycle used to analyze the formation of an ionic compound from its constituent elements. The Born-Haber cycle is a cycle of enthalpy changes of the processes that leads to the formation of ionic crystalline solid compound from elemental atoms in their standard state and the enthalpy of formation of the solid compound. The importance of this Born-Haber cycle is in the theoretical determination of the lattice energy of an ionic solid. We can move on to further details of the Born-Haber cycle. There are several steps in Born-Haber cycle. In the formation of mx solid from m solid and x2 gas, as represented by this equation, m solid plus half x2 gas gives mx solid. There are several steps. There are several enthalpy changes, and identifying that enthalpy changes and connecting that enthalpy changes together, we can get a thermodynamic cycle, and that cycle is termed as the Born-Haber cycle. We are just sifting through various steps now, and after that we can construct the Born-Haber cycle. The first step in this reaction is the sublimation of the solid metal. You know, the metal is initially present in the solid state. It has to be sublimed to the gaseous state metal atom. So, sublimation means the conversion of a solid substance into the gaseous state without moving through the liquid state. So, the first step is the sublimation of the solid metal. This step involves converting a metal solid M into individual gaseous metal atoms M gas. The energy change that happened during this transformation is called sublimation enthalpy, abbreviated as delta H sublimation. So, the first step in the Born-Haber cycle during the formation of ionic solid Mx as per this equation is sublimation of the solid metal. The second step is the ionization of the metal atom. The metal is now converted to gaseous atoms, and it has to be ionized to produce the positive charged metal ion. The metal atom loses an electron to form a positive ion, and there is an associated enthalpy change or energy change, and this energy is known as ionization enthalpy, abbreviated as delta SIE. The third step in the reaction is dissociation of non-metal molecule. The non-metal molecule is initially present as X2. It has to be dissociated to X atoms. So, the non-metal is often a diatomic molecule like a chlorine that needs to be broken into individual atoms. This is the bond dissociation enthalpy, the energy change that occurs during the dissociation of X2 into X atoms is nothing but the bond dissociation enthalpy, which is abbreviated as delta H dissociation. The fourth stage is the electron affinity of the non-metal. You are familiar with the fact that electron affinity is the amount of energy released when an electron is added to isolated gaseous atom. The non-metal atom gains an electron to form a negative ion. That is, X gas is now you are having, that X minus accept an electron and converted to X minus gas. This process is exothermic and the energy released is known as electron affinity, abbreviated as delta S EA. The last step in the Born-Haber cycle is the formation of ionic lattice. Finally, now you are having M plus gas and X minus gas, and the metal cation M plus and non-metal anion X minus combine together to form ionic solid MX. The energy change, the energy released during this process is the lattice energy U. So, we have discussed 5 important steps that may occur during the reaction of M solid plus half X2 gas to get MX solid. These 5 steps are associated with some enthalpy changes or energy changes that can be connected and represented together in the form of a cycle which is known as the Born-Haber cycle. The heat of formation is very important as far as the Born-Haber cycle is concerned. The heat of formation of MX solid, which is abbreviated as delta H0F from metal M and X2 gas, can be experimentally measured. So, heat of formation is an experimentally measurable quantity. According to Hess law, delta H0, that is total enthalpy of formation or total enthalpy change, is related to the enthalpy changes mentioned in the above steps, as total enthalpy change is the sum of enthalpy changes occurring in the individual steps. Thus, according to Hess law, which states that the total enthalpy change of a chemical reaction remains the same whether the reaction happens in a single step or through a number of steps. The total enthalpy change is delta H0F, which is equal to sum of the previously mentioned 5 energy changes. That is why we can represent a cycle in which total enthalpy change delta H of 0 as a sum of individual enthalpy changes belongs to 5 steps that we have just discussed previously. The Born-Haber cycle for the formation of MX solid from M solid and X2 gas can be represented like this. That is, initially we are having M solid and half X2 in gaseous state. They have to combine together to produce MX solid. The enthalpy change, the total enthalpy change during this transformation can be represented as delta H of 0. This is the overall enthalpy change. Now, we can split this reaction into 5 steps that we discussed previously. First of all, M solid undergo sublimation to convert M gas. The energy change that occur here is delta H sublimation, which is known as enthalpy of sublimation. M gas now converted to M plus gas. You know, this stage is ionization, and the enthalpy change that occur here is delta HIE or ionization enthalpy. So, metal is first converted to M gas, that is sublimation, M gas converted to M plus gas, that is ionization. So, 2 energy terms and 2 steps are already completed. Now, half X2 gas dissociated into X gas. The energy change during this transformation is delta H dissociation, but not full delta H dissociation is required because we are having only half mole of X2. When X2 is converted to 2X, the enthalpy change is delta H dissociation. But here we are having only half mole of X2. So, the energy change occur here is half delta H dissociation, half delta H dissociation. Now, this X gas is converted to X minus gas. The change occur here is capturing an electron and the energy released is electron affinity. So, the energy change that occur during this transformation is delta H EA or electron gain enthalpy. So, 1, 2, 3, 4. 4 steps are already completed. Now, there is one more step, that is the last step in the Born-Haber cycle, that is the conversion of M plus gas and X minus gas to MX solid. That is M plus gas and X minus gas combine together to produce MX solid. The energy change that occur here is the lattice energy U. So, this process, this reaction, that is M solid plus half X2 gas gives MX solid, is splitted into 5 different steps. The total enthalpy change is delta H0. Total enthalpy change is the sum of 5 kind of enthalpy changes or energy changes. That is as per the Hess law of constant heat of summation. So, all these energy changes can be coupled together to get an equation, and this thermodynamic cycle is called Born-Haber cycle. Now, we are discussing the calculation of lattice energy from the previously mentioned Born-Haber cycle. From the Born-Haber cycle, for the formation of MX solid, we can write as per the Hess law, the total enthalpy change delta H0 is the sum of enthalpy changes belongs to 5 steps. So, we can write this equation delta H of 0 equal to delta H sublimation plus delta H ionization enthalpy plus half delta H dissociation plus delta H EA or electron gain enthalpy plus U. So, on rearranging this expression, you can calculate U by putting all other parameters on the left hand side. You are getting U is equal to delta H0 minus delta H sublimation plus delta H IE plus half delta H dissociation plus delta H EA. So, this allows the calculation of lattice energy. So, Born-Haber cycle is a cycle used to calculate the lattice energy of an ionic crystal theoretically. By knowing all these parameters shown in the right hand side, it is easy to calculate lattice energy of an ionic crystal, because the experimental determination of lattice energy is a difficult task. So, in that scenario, the application of Born-Haber cycle in the theoretical calculation of lattice energy is highly relevant. Now, illustration of Born-Haber cycle. Consider the formation of sodium chloride gas from sodium solid and Cl2 gas as depicted by this equation. Sodium solid plus half Cl2 gas gives NaCl solid. There are various steps as we discussed in the case of MX solid. Here also there are 5 steps. In the 5 step, sublimation of the sodium metal being the first step. Sodium atom sublimes to gaseous sodium atom by absorbing heat energy. The energy change that occur during this transformation is abbreviated as delta H sublimation. The second step is the ionization of metal atom. The gaseous sodium atom absorbs ionization energy, which is delta Si, and release one of its electron to form a gaseous sodium ion Na plus gas. Third stage is the dissociation of the non-metal molecule, that is dissociation of Cl2 molecule. Diatomic gaseous chlorine breaks into 2 individual atoms by absorbing bond energy such that chlorine atom absorbs half of the bond energy of the chlorine molecule, that is abbreviated as delta H dissociation. It should be noted that when a Cl2 molecule is dissociated into two chlorine atoms, the overall energy change is delta H dissociation. However, in the formation of NaCl solid, there is only one chlorine atom participating. So, as far as the energy is concerned, dissociation energy is concerned, we need not to take delta H dissociation completely. This is for the formation of two chlorine atoms and only one chlorine is participating in the reaction. So, the energy term involved in the reaction, in the formation of NaCl is half of delta H dissociation. The fourth stage is electron affinity of the non-metal. Chlorine atom accepts an electron to form a chloride ion and release energy equivalent to electron affinity, which is abbreviated as delta H Ea. This is the last stage, that is the formation of ionic lattice of NaCl. Gaseous sodium ion and gaseous chloride ion combine together to form solid NaCl molecule and releases energy equivalent to the lattice energy. Now, the heat of formation of sodium chloride delta HF0 from the sodium metal and chlorine gas can be represented as Na solid plus half Cl2 gas gives NaCl solid and the overall enthalpy change is delta HF0, that is nothing but enthalpy of formation of sodium chloride. This enthalpy of formation of sodium chloride delta HF0 is the overall enthalpy change during the conversion of sodium and chlorine to NaCl solid. So, this enthalpy of formation can be splitted into 5 components, belongs to 5 steps we have just discussed now. Now, it is possible to represent the Born-Haber cycle for the formation of NaCl as shown here. The reaction between sodium solid and half Cl2 gas to form NaCl solid is associated with an overall enthalpy change of delta HF0. This is splitted into several steps. In the first step, sodium solid converted to sodium gas. Energy change involved is delta H sublimation, known as sublimation enthalpy. Sodium gas converted to Na plus gas. The energy change involved is delta HIE or ionization enthalpy. Similarly, Cl2 first converted to Cl atom in the gaseous state. The energy involved is half delta H dissociation or half of dissociation enthalpy. Cl gas converted to Cl minus gas, and this transformation is associated with an enthalpy change abbreviated as delta H Ea and is known as electron gain enthalpy. Now, the fourth step is already completed and 4 type of energy changes are here also. They are delta H sublimation, delta H ionization, half delta H dissociation and delta H electron gain enthalpy or electron affinity. Now, you are having Na plus gas and Cl minus gas together. In the last step, Na plus gas and Cl minus gas combine together to produce the ionic solid NaCl, and the energy change that occur here is lattice enthalpy U. This is the Born-Haber cycle for the formation of solid sodium chloride from sodium metal in solid state and Cl2 in the gaseous state. This is a more legible representation of the Born-Haber cycle for the formation of sodium chloride. All the 5 sub-steps and the entire step is shown here. So, the overall enthalpy change being delta H formation, which can be represented as a sum of all the 5 steps and their energy changes. Now, calculation of lattice energy. From the Born-Haber cycle for the formation of sodium chloride solid, we can write this expression as per the Hess law. Delta H of 0 is the sum of 5 components, that is delta H sublimation plus delta H IE plus half delta H dissociation plus delta H EA plus U. On rearranging, we will get the value of U as lattice energy as U is equal to delta H of 0 minus of delta H sublimation plus delta H IE plus half delta H dissociation plus delta H EA. And it is possible to calculate the lattice energy of the ionic crystal NaCl if you are knowing the parameters shown in the right hand side of this equation. Now, we are discussing solubility of ionic substances. The solubility of ionic substances in a solvent, typically in water, is determined by the balance between lattice energy and hydration energy. High lattice energy means stronger ionic bond, making the substance less likely to dissolve in water. Hydration enthalpy is a very crucial parameter that governs the solubility of ionic substance in water. Hydration energy is defined as the energy released when gaseous ions are surrounded by water molecules, and when an ionic substance is put in water. For example, if you are taking some NaCl and dissolve in water, Na plus ion as well as Cl minus ion will be surrounded with water molecules due to some electrostatic interactions, and the energy released during that surrounding of water, during that covering of water on each ions is called hydration energy or hydration enthalpy. Now, for an ionic substance to dissolve in water, the energy released during hydration, which is abbreviated as delta H hydration, must compensate for or exceed the lattice energy, that is U. That is, an ionic substance is soluble in water if and only if delta H greater than or equal to lattice energy U. If hydration enthalpy is less than lattice energy, the ionic substance will not dissolve in water. Factors such as temperature, polarity of the solvent, nature of ionic compound, etc. will also govern solubility. Even though this is the situation, the most crucial factor is the magnitude of hydration enthalpy or hydration energy and lattice energy. The hydration enthalpy must have an edge over lattice enthalpy for the ionic substance to dissolve in water. Now, partial covalent character of ionic compounds. Ionic compounds are not 100% ionic. Many of the ionic compounds exhibit partial covalent character, and this partial covalent character is due to the polarization of ions. What do you mean by the term polarization? The distortion in the electron density of a negative ion under the influence of a positive ion is known as polarization. Such a polarization factor leads to covalent character in ionic compounds. The degree of covalent character in an ionic compound is governed by Fajan's rules, which describes polarization and covalent character. These are Fajan's rules. The first statement is a small positive ion favors covalency. The second statement is a large negative ion favors covalency. High charge of either sign favor covalency is the third statement of the Fajan's rule. And finally, polarization and hence covalency is favored by positive ions that does not have noble gas configuration. You have to keep these four important statements of Fajan's rules to assess the covalent character of an ionic compound. The Fajan's rule is mentioning covalency of each and every ions based on size of the ion, based on the charge of the ion, based on the configuration of the ion, etc. Partial covalent character of ionic compounds can be governed with the help of Fajan's rules, and based on the Fajan's rules, it is possible to compare the covalency of ionic compounds. For example, NaCl, that is sodium iodide, is more covalent than NaBr, which is again covalent than NaCl and which is more covalent than NaF. This is because this is the order of increasing covalent character. This can be related to Fajan's rule. There is I minus, Br minus, Cl minus and F minus. A small cation favor covalency, a large anion favor covalency. Here cations are same and anions will control the covalency. I minus is the large ion favor covalency. So highest covalent character is associated with sodium iodide. MgCl2 has greater covalent character than NaCl. This can be based on the fact that magnesium is in 2+ state, that is high charge. It is a small cation. Both the factors favor covalency, so the result MgCl2 has greater covalent character than NaCl. Now we are discussing some problems based on the concept we have studied. The first problem is construct a Born-Haber cycle for the formation of MgO solid from magnesium solid and oxygen gas. We previously learned the general Born-Haber cycle for the formation of MX solid and for the formation of NaCl solid. The same concept can be applied to develop the Born-Haber cycle for the formation of magnesium oxide solid from magnesium metal in solid state and oxygen in the gaseous state. This is the Born-Haber cycle. Here you can see magnesium solid which combine with half oxygen gas to convert it to magnesium solid. The overall enthalpy change, as in the previous case, it is equal to delta H of 0. So we can split this entire reaction into 5 steps. The steps are sublimation stage, ionization stage, dissociation stage and electron affinity stage, followed by the combination of Mg2 plus and O2 minus to convert it to MgO solid. The energy involved is lattice energy. This diagram is constructed based on the principle what we have adopted in the case of the Born-Haber cycle of NaCl and MX solid. Now some MCQs are here. The first one, which of the following compounds will have least covalent character according to Fajan's rule? These are the options NaCl, MgCl2, aluminum chloride and beryllium chloride. Your answer is NaCl. This is direct application of the Fajan's rule. Another multiple choice question is, which ionic compound is likely to be more soluble in water? These are the options. Option A, compound with high lattice energy U and high enthalpy of hydration delta H hydration. Compound with low U and high delta H hydration. Compound with high U and low delta H hydration. Compound with low U and low delta H hydration. It should be noted that for an ionic substance to be soluble in water, delta H hydration must be high and lattice energy should be low. That is, delta H hydration have some edge over the lattice enthalpy U, and hence your answer is option B, compound with low U and high hydration enthalpy. That all about the present module. Have a nice learning experience. Thank you.